Hello, and welcome to quantitative electrochemistry. We can think of this like stoichiometry, but applied to electrochemistry. So, like Pivner goes with gases, molarity is moles over liters, or we can use grams by using or get to grams by going through molar mass. This is going to be how do we figure out quantities and amounts, but with electrochemistry. All right, so now would be the time to hit pause, get out your notes. It's our 3A notes, and it's on page 15. And we're going to talk through the analogy that I have here. So if we think of electricity like a current, and so when we think of a current, we think, right, of a river running downstream, right, or of an ocean current, water moving. Okay. The faster the water moves, the faster the current. And this is going to be the same with electricity, except for these aren't going to be, this is going to be water moving. This is a river of electricity. So if we think of these wavy lines instead of being electricity. Okay, so it's the flow of electrons, usually through a wire, or it could be through a solution or something like that. Okay. So this is your current, and current is I. That's the symbol for current in chemistry, and it's measured in a unit known as amperes. The other thing that would be really helpful to get out is if you hit pause, and then you can get out your equation sheet, the blue equation sheet, because all of the values that you need are going to be on the back page of that on the bottom. So there's a little section on electrochemistry. And we'll be talking about some of those units and values. So we said I, again, is the current, and I've got a little image here of like flowing electrons. Okay, so it's moving downstream. Okay, that's the movement of electrons, and we measure this in a unit called amps. Okay, so resistance is the next term we want to talk about. Resistance is not officially testable in AP chemistry, but I think it's kind of important to understand. So resistance is like a dam. Well, what happens if you have this flow of water, right? You have this water and it's headed this way, and then all of a sudden it hits a barrier, it hits a dam. This dam would be the resistance. And if you've taken physics, you know resistance is measured in ohms. We're not really going to worry about that because that's not really in chemistry. But what resistance does is it holds back the flow of the water. And in chemistry, resistance would be it stops the flow or slows the flow of electrons. Things that have really high resistance values are things that are going to be insulators, so plastics. Okay. Things with low resistance, so things that tend not to have this barrier here, right, or have a very short barrier, right, that the water can go right over, would be things like metals, graphites, aqueous salts. So in terms of water, gravity is a force which pulls the water downstream. So that's in our analogy. In terms of our electrochemistry, voltage is the force that actually pulls the electrons from one place to another. So like, why is the water actually moving? Well, it's because gravity is pulling it down, right? Water always travels downstream or generally travels downstream. In our case, why does it move from one thing to another thing? So why does it move from the anode to the cathode? That's because there's a difference in values and the E cell values, and then that would create that. Or you've put a battery, right? So that'd be like forcing it to go upstream, right? So if you think about like a water analogy, if it has a positive E cell value, so let me write this down. So in terms of like actually making the water flow, like what's actually pushing it down the stream, what's like causing it to move, that would be in our case, that would be your voltage. And even if you have a dam, if there's a little opening or whatever, the voltage is what pushes it through those holes. or the space or the opening, or it just pushes on the resistance, right? So pushes on like the dam, right? Just because water is dammed up doesn't mean it's still not trying to push through. It just depends on how strong is your dam, how strong is your insulator versus how strong is your current. Okay, so our voltage is trying to move it downstream. Okay, resistance may or may not be blocking it depending on how strong it is. And so when we think about our E cell values, a positive E cell value, okay, standard cell, which would be a negative Gibbs value. We always want to keep saying that. So negative Gibbs value. Both of these are telling you that your water is traveling downhill, that you are producing voltage and the current is moving along. You have enough energy to just naturally, it just does it on its own. You're downstream. Okay. And so that voltage is just going to push it on down no matter what. With something which has a negative E cell value, so our electrolytic cell, positive Gibbs. Well, now we're not trying to go downstream. We're actually trying to go upstream. So we're sort of going against the flow of things. So if you imagine like you have water and it's coming downstream and you're trying to push it back up, your boat back upstream, you're going to need something to do that. It's not naturally just going to occur. So maybe you need a motor in our analogy, or you need a paddle, or you need something. In this case, the need that we need is going to be some sort of power source, or you're going to need a battery. And we saw that in our electrolytic cells lab. So these are important factors to understanding the components that go into creating the currents and why we see some of the things that we see. So how is this going to actually connect to stoichiometry? Okay, so before we get into the calculations, we need to talk about the last type of cell. So these types of cells are electrolytic cells. So these type of cells will have a negative E cell value. They will have a positive Gibbs value, which means we need to put electricity in. Okay. Where they're different than electrolytic cells is that they are electrolytic cells, but they're a specific type and they have a specific purpose. And that's where this word plating comes in. So what it means to plate something is to basically put a thin coating on the outside of something else. And this is very applicable to the real world because let's say, for example, you want something golden, but you can't afford a solid piece of gold. Well, you can take a piece of cheaper metal and you can use electricity, so that's the electro part, okay, to put a thin plating or coating. Plating is just another word for coating of gold on the outside. So it looks gold. It wears the same as gold because gold's what's on the outside. But if you were to cut the piece in half, you would see that you don't have gold the entire way through. This is also very practical, speaking of gold, because white gold, for example, is not actually gold on the outside because gold can never be white. So I always think it's funny when I hear white gold because I think, how can that happen? So white gold is jewelry, so such as a ring, and you have gold on the inside of the ring, and then they put a very thin coating of rhodium on the outside. So they do that through electroplating. They put a very thin coating. Okay, this will be the inside and the outside, right? And so what you are actually seeing is the rhodium metal, or I believe they can also use palladium on the outside. So the golden part is actually not exposed. It's on the inner part of the gold. And so that's how you get white gold. So electroplating, again, we said is an electrolytic cell, meaning it requires electricity. Okay, so when we look over here at the cell, we have our battery and we have the anode, which is where oxidation takes place. We have a cathode, that's where reduction takes place. Too high on the screen, reduction. Okay. And so we have just our normal electrolytic cell. What's different about electroplating, excuse me, is that electroplating, what happens at the anode is what happens at the cathode. And I'll explain why it's done this way in a minute. So what I mean by that is at the anode, you have gold metal. So you just have like a hunk of gold, electrode, a piece of it. In solution, you have Au3+. So you have both the Au and the Au3+. And over here, you put whatever object you want to get plated in gold. Okay? So what's unique about electroplating is that at the anode, the Au, so this is our reaction at the anode, the Au metal loses 3 electrons, becomes gold 3+, and so I'm going to draw the arrows because this is going into solution. So this will get smaller as your cell runs. And then if we look at the cathode, that's where these Au3+ will come and form Au, the metal, and that's how you get it coated. Okay. All right, so cathode would be, it's basically just going to be the opposite reaction. So could you possibly electroplate something with just a normal electrolytic cell? And you could even set up a galvanic cell and do some types of plating. That one probably wouldn't be quite as effective, just because you could run the chance of like secondary reactions taking place, because you don't have electricity in there to control the reaction. But the reason why you want it to be Au3+ here and Au here is that then the concentration of the solution stays constant, which means you get a really nice coating on the outside and you can control the layer. And so, if you start out with this and then you didn't have the Au3+ here, or you have Au to go to Au3+ here, what would happen is the molarity of the Au3+ would drop, and then whatever metal you had here would basically pollute your solution, and so you would have impurities in here. And so by having the same reaction at your anode and your cathode, you're ensuring that it stays pure Au3+ and Au throughout the entire process. And so this is a special type of electrolytic cell used for coating of things, especially in precious metals, but it can also be used to like coat zinc and coat some other things. So what if we think about an example that we've actually seen in class? So we're going to pause it, you can think about it. But an example that we've seen is the pennies that we did. Okay, so the pennies were zinc on the inside, but they had copper on the outside. And the way that they did that was they make what are called blanks of zinc. So that's this on the inside. And then they put it into a bath and then it coats the outside. So an electrolytic solution, and it will coat the outside in the copper. And they can control how much goes on there and they can get a nice thin coating. So this definitely has a lot of really awesome practical applications. Okay, so now we know the setup for the electroplating solution, okay? And that was for practice problem number 1 on page 15. And now we want to talk about how much time is required to electroplate 0.5 grams of gold using a current of 6 amps. And this is where we get into a brand new equation. We've never seen this one before, but it's on the back of our equation sheet. So we see an equation. We're going to need 2 values. We're going to need I is Q divided by T, okay? And then we're also going to need Faraday's constant. So we've actually been using this. This is Faraday's constant. And you're going to notice, hey, I know this one. 96485 coulombs per 1 mole of electron. So where this value, Faraday's constant, comes from is the charge on one electron is 1.062 times 10 to the negative 19, but that's one single electron. We're never going to use one single electron. And more importantly, when we look at balanced chemical equations, they're not in singular electrons or singular atoms. They're balanced based on moles. That's what the unit for the coefficient is. So we need to be able to relate to not just charge, but the charge on a mole of electrons, and that's going to help us. So if we come back over here to this equation, let's look at what we've got. And what's great on the equation sheet is not only do they tell you what all of these things are, they give you the units, which is so nice. So I, we said before, is current. That's the flow of electrons. So that's how much charge you're getting per second, basically. So this is measured in a unit called amps or amperes. Q, oh, we've seen Q before too. Guess where Q comes from that we've seen? Coulomb's law, right? The charges. We didn't really solve that one, but we saw that one. That's charge, and that is measured in a unit called, oh, coulombs for Coulomb's law. And then, hey, it's all coming together. T is for time, and that's measured in seconds. It has to be in seconds. So if you're given minutes, you gotta change it out. Okay? All right. So this is everything we need to solve this problem. Okay. So our question reads, how much time is required to electroplate 0.5 grams of gold using a current of 0.6 amps? Well, what do we have and what do we want? Because that's going to be very important to establish. So we know the amps, so we know this, right? And we want to know time. So we can't use this equation right now because we only have one thing and we're trying to solve for another thing. We need to somehow be able to figure out charge. And that's where Faraday's constant is going to relate. So I'm going to rewrite the half reaction for gold. And you can do either. For electroplating, you can write either reaction. I'm going to write the reduction, but it really doesn't matter because it's basically the same reaction, just written, flipped over. Okay? So I want to make 5 grams of gold. And we said all these equations here, this is the stoichiometry of electrochemistry. So we have 0.5 grams of AU that we want to make. Okay, well, if I want to get charge, the thing that I have for charge is electrons. So I can't convert until I get AU out of grams and into moles. So I'm going to use the molar mass, which is 197 grams into 1 mole. Both of these need labels. Okay, so that's a mole conversion here. Now, in order to do stoichiometry, we have to use the balanced chemical equation, and we're converting substances. So we're going to put 1 mole of AU on the bottom, and we're going to put 3 moles of electrons on the top. Because if we want to deal with charge, we have to deal with electrons, right? Electrochemistry deals with electrons. Transfer of electrons. Okay, well, I can't plug moles of electrons in for charge yet, but hey, look, Faraday's constant is going to help me out. So what I can do is I can say, okay, well, 96485 coulombs is equal to 1 mole of electrons. Oh, now I'm out of moles of electrons, okay, and I'm into coulombs. And guess what? Coulombs is our charge. All right, so we get 735 coulombs. Well, how can we plug this in? All right, so for amps, the problem tells us we have 0.6. So see, now that I have charge, now that I have this, I can plug it into the equation and solve for time. So I have 0.6, and this is equal to charge, 735, and then we're going to put T here, So you can't solve for the unknown when it's trapped in the bottom. So I'm going to multiply both sides by t. So I'm going to cross this out. I'm going to multiply both sides by t. So if I multiply by t, it cancels out here. And we add it over here. And then in order to solve this, the next step would be to divide both sides by 0.6. Cancels out this. Okay, so we have this divided by 0.6. And we get, whoa, 1, 2, 2, 4 seconds. So if you wanted, you could do minutes divided by 60. And that's basically equivalent to, I just divided by 60 to get it in minutes, about 20 minutes. So to get half of gram gold plated on the outside of this using 0.6 amps, it would take you about 20 minutes of waiting. So I'm going to end the video here. If you feel confident and ready to move on to the next problems using these techniques, you can move on to page 16 and 17. And problem 18, you have to do a little bit of problem solving. But I want to just say one thing before you move on. These calculations that we just did, they don't just work for electrolytic cells or electroplating. These can be used for anything. So anytime you're given current and time, and you're able to get the charge, you can always get the charge from the half reactions. You can do that for any half reaction. You're able to do this. So maybe a galvanic cell, instead of saying, how much current are you going to use, you could figure out how much current you're going to produce for one of these. Okay. So it does not necessarily have to be a electroplating situation. This was just the application that we did for this first one. So if you're stuck, I'm going to record one more video. And in that video, I will go through another problem or two. And you can either work along with me, or you can pause it and you can try to do it for yourself, and then see if you're able to get it correct at the end. Okay?